Let me start the recording. And there we go. All right. Happy Monday. Welcome back. So we're going to do like another day or so of modular arithmetic stuff. And that's going to result in a smooth sliding into our next topic, which is something called group theory, which isn't in the textbook. But we've been doing group theory all along anyhow. You've been doing group theory ever since like kindergarten, first grade, when you started to add and subtract. You just didn't know it was called that. So last time we took a little look at how a modular system can be used to safely encrypt data. So what we did was fairly easy. So on the homework, if you decoded it and you could read it, you're right. If you decoded it and it's gibberish, you were wrong. So anybody have any questions about any of the homework or anything? Or from any homework, not just that one?
I was really stuck on number 2 from the most recent one, from the decoding one. I kept getting something that doesn't make any sense.
Well, you know me well enough by now that it's possible and you know, I know you well enough to know that you probably did it right. So number 2. Where's number 2?
Yeah, the one that's like shift 10 mod 43.
Oh, and so it just came out to be gibberish?
Yeah, I kept getting space, TKAY space, and I don't know, but do you know what it was supposed to be? Maybe I could see where I messed up.
Oh, you know what? I'm willing to bet that first letter T should have been an O.
I got TKAY also.
Oh,
too.
Yeah, okay, you did it right. I messed up.
Okay.
Yeah, that T should have come out to be the letter O, and it should say okay. Yeah, I probably just did something wrong there. But anyhow, sorry about that.
No worries. I just wanted to figure out if I was doing something wrong. Thank you.
No, so sometimes when I probably didn't sing the alphabet song and I counted wrong with that shift 10 kind of thing. I may have mentioned a whole bunch of years ago, one of my students in this class wrote a little, I think it was Java, a little applet that you could type in like an English sentence and it would just spit out the code in blocks of 6, and you specify the mod and the shift. And he also had the inverse operation where you type in the numbers and it just reads it back in English. And at some point when the college updated our laptops or something, that whole little applet got lost, and I really kind of miss it. So so some of you I know are probably headed into sort of cybersecurity and things like that. So this pretty straightforward, easy code system that we did by hand, even though I messed up on that one, just this simple thing is very, very secure. Maybe not for like military secrets or something like that. So some of you will be learning some other methods of this along the way, and it can get a lot more sophisticated. And there's other methods of doing encryption as well. There's one that uses matrices. I'm assuming you've seen matrices somewhere along the way, just rectangular arrays of rows and columns of numbers. There's a way of doing matrix multiplication that will also encode things. But the RSA, the RSA public key stuff that this forms the basis of is very common out there because it's really easy to program and impossible, nearly impossible to break. All right, so let's see here. So today and Wednesday will bring us probably to the end of the modular arithmetic stuff, but I'm going to slide into something called group theory. And we have spring break coming up pretty well too. It's the week of the 22nd. So I think that's after next week. When is spring break? Let me look at my calendar here. Whoops. Oh, there we go. Yeah, so this week and then next week, and then we're off for a week. So that'll be kind of nice. All right, so what we're going to look at today, have any of you, especially those of you in computer sciences, have any of you heard the expression Chinese remainder theorem? Anybody ever heard that? I think sometimes it gets abbreviated as CRT. Does that ring a bell with anybody? Yeah, well, we're going to take a look at that next time. And it has some applications as well. So today we're going to look at inverses. Whoops. Multiplicative modular inverses. Next week when we start group theory, we're going to take out the word modular and we're going to look at things like inverses and that. Now the word multiplication, when you hear the word multiplication, like most people, you think of, 3 times 7 equals 21. But the word multiplication has a much broader meaning. Multiplication can be used just to express a generic, what's called a binary operator. So a binary operator takes 2 elements from a set, and it's a rule for how to combine those to produce a third element in that set, which is at the heart of group theory. So we think of addition and multiplication, but addition is even a weird sort of binary operator as well. So from the old days, so an inverse, let A be an element. Let A be an element in a set. I'm going to drop the word set when we hit group theory and just call it let A be an element in a group. A group has a specific mathematical meaning. And let an asterisk be a binary operator. So instead of using the X for multiplication, we're just going to use a star because we can define it certain ways. And let E be the identity element. So A is an element of a set of objects. B is a binary, in this case, for today, a binary multiplicative operator. In other words, this is the times sign. And E is the multiplicative identity element. Now, inverse. So again, the word multiplicative goes in front of here, but I'm not writing it because we're going to have a more generic thing. Now, then, so that's the definition of an inverse. You have an element, and assuming the existence of the multiplicative inverse, then A times A inverse equals E. So that looks sort of abstract right at this point, but I'm going to tell you where you've been doing this for a long, long time, as soon as I have some coffee. Oh yeah. All right, so we have these four symbols. A is an element. This is the multiply sign. E is the identity element. And you already know that an exponent of -1 actually represents inverse in all situations, although inverse can have a couple of meanings. Also, and so what's the difference between these two? The very subtle difference. From here to here, what property did I just use? What's the property I just used from here to here?
Commutative?
Yeah, that's the commutative property. We take that for granted. So this says multiply on the right or multiply on the left, you still get back to the identity element. Now we take commutativity for granted, but commutativity is actually a rare thing out there. So we think nothing of saying 6 plus 5 is 11, also 5 plus 6 is 11. Or 2 times 9 is 18, 9 times 2 is 18. We just think, well, of course it is, but it's actually very rare to have something called commutativity. How many of you have ever worked with a matrix? You know, the rectangular array of numbers. Anybody worked with a matrices before? Like you learn to add them and multiply them. Anybody done that?
Yes.
Yeah, probably in pre-calc, I'm guessing, right?
Yeah.
Yeah. So when you add two matrices, if you have two matrices A and B and you're adding, they can be commuted. But when you multiply two matrices, matrix A times matrix B, if you try to do matrix B times matrix A, you could get a different answer, or you could have no solution at all. So, and same thing with vectors, because matrices are just rows and columns of vectors. So commutativity is rare, but when we're talking about multiplicative inverses, you can always do that. So let me give you an example all the way back to grade school, and you're going to go, oh, this is what we're talking about. Fix this. See, we're going to work with so our set of objects is going to be real numbers. In other words, the x-axis. So real numbers, whole numbers, rational numbers, fractions, irrational numbers, anything but imaginary numbers. Then E, the multiplicative identity, identity, E is, so the multiplicative identity when we're working with real numbers is 1, right? 1 times anything is anything. So if A is any real number, then A times 1 is equal to 1 times A is equal to A. It's called the identity because when you operate it on, now here I'm using the regular multiplication sign because that's where we are right now. So multiplying by the identity is also always commutative, always, even if other stuff isn't. So that's the identity. So the inverse of A takes you back to 1. So if we let A equal 5, then A inverse is, well, in this case, that -1 allows us to write the inverse in a certain way. So what's the multiplicative inverse of 5? In fact, we usually think of this exponent as doing what?
Flipping the fraction.
Yeah, we think of it as I always, when I'm teaching like the lower level algebra, the remedial stuff, I always refer to the -1 exponent as the turn it upside down exponent. No, when you're working with regular numbers, the -1 just turns it upside down. And so this would be 1/5. The reciprocal upside down. And then we have 5 times 1/5 is equal to 1, and 1/5 times 5 is equal to 1. So that's what an inverse does. So on that previous thing, when I had A star A inverse equals E, that's what it is. Inverses, and it doesn't matter which one you call the inverse, by the way. 5 is the multiplicative inverse of 1/5. So it doesn't matter where you put the -1, but you can only put it once. So multiplicative inverse is just that. It is the object of your set that takes an element back to the identity. So this is a simple one on here. So true or false, every real number has a multiplicative identity.
False,
Yeah, why?
because you can't do like the inverse of 0.
That's right. So 0, out of all the infinity of real numbers, 0 is an element that has no multiplicative identity. So sometimes numbers have them, sometimes they don't. 0 is the only exception in this case. In other sorts of systems or groups, we'll see that that's not always the case. So the idea of a multiplicative inverse is pretty straightforward. I just gave it to you in like official language here. So we're going to look at modular inverses. And the word I'm leaving out for the rest of the day is multiplicative modular inverses. We're only going to worry about those. Well, I'm going to write a little multiplication table to start out, and then we're going to look at some other examples here. So in modular systems, no matter what mod we're working with, mod 11, mod 1025, 0 also has no modular inverse. So modular inverses, E, the multiplicative identity is still 1. Oh, and by the way, E stands for the German word for identity. It's Einheit. So the E actually does stand for identity. It's just German. So in every modular system, 1 is the multiplicative inverse. So let's look at a mod 5 table. I'm going to put the 5 there just to remind us. So in mod 5, those are the only non-zero, those are the least residues mod 5, and we leave 0 out. So when we multiply, we go in this direction. So 1, 2, 3, 4, 2, 4, 1, 3, 3, 1, 4, 2, and 4, 3, 2, 1. So when we multiply in mod 5, now 5 is not only odd, it's prime. If you have a modulus that's not prime, odd or even, it's possible that there's no inverse. So we see from this table inverses. So here, oh, and because we're using a prime number, the 4 elements of this system show up exactly once in every row and every column. That's why prime numbers are so important. So inverses. So we see that 2 times 3 is equal to 1, and 3 times 2 is equal to 1. So 2 times 3 is 1, 3 times 2 is 1. Modular multiplication is commutative in the systems we are. So this means that 2 and 3 are multiplicative inverses of each other. For 4, you look over here, 4 is its own inverse. 4 times 4 is 16, which is 1 mod 5. So 4 is its own inverse. And, oh, also, E times E is always E because it's the identity. So these are the inverses in mod 5. So that's how it works. It's whatever you multiply that takes you back to the number 1. Questions or anything yet? It's pretty straightforward, except for all that fancy vocabulary I used for a while.
So when you say E is equal to 1, does that mean like just in this one instance it's equal to 1, or is that just something that is always going to be 1 because it's inverses?
For us, for our modular inverses, the multiplicative identity will always be the number 1. Because when you're doing mod multiplication, you're still multiplying real numbers. We're just multiplying integers, but in this weird closed mod system. So the identity element for modular inverse is always going to be the number 1.
Got it.
As long as you brought this up, let me do a thinking problem. Suppose we have, let's look at a set of things that's not numbers. All right. So let's look at sound frequencies. So instead of our numbers, all of our elements, the A's, are specific frequencies of sound. So if you add a sound frequency to a sound frequency, what do you get? You get another
sound frequency.
So a sound frequency plus I'm using the word plus now. A sound frequency plus a sound frequency results in another sound frequency. You can't add your way out of the universe of sound frequencies. So I'm using the word addition now, but that's okay. What would be the identity when we are adding frequencies? A sound frequency plus what will give you back that same sound frequency? What would be the identity element that doesn't change anything? Oh, thinking, aren't you?
Just silence or just...
Nice. Yeah. So silence is the additive identity for sound. A sound frequency plus silence just produces that same sign, that same frequency, right? So that's the identity. So given a particular frequency, what would its inverse be? In other words, what would you add to a frequency to give you silence? And where do we hear about this where is this in the real world? So what can you do to a sound frequency? What can you add to it to produce silence?
Isn't it like the same frequency? Like that's how noise canceling headphones work?
Oh, Carlos, perfect. I was thinking noise cancellation, right? So noise cancellation, it works by adding, I'm going to say like an opposite frequency that cancels it out. And I'm not a physics kind of person, but so sound frequencies travel like this, right? So if you add another sound frequency, you can actually cancel that wave motion out. So if you've ever watched like at the ocean or something, when you get currents where wave systems are coming at each other at an angle, they cancel each other out. Another example of this, if you've ever been in an outdoor concert, okay, and you walk parallel to the stage from one side to the other, as you walk, that sound gets louder and softer and louder and softer because the speakers are sending out sound waves. They're sending them out in kind of like a V shape. And where those sound waves cross, the trough, when the trough of one wave meets the crest of another wave, they cancel out. So that's why if you walk parallel to a sound stage, you'll hear that noise, the volume kind of appear to go up and down and up and down. So excellent, Carlos, yeah. So the inverse frequency cancels it out and you get silence. Okay. If we have, so let's look more at this inverse thing. Coming up with them can be kind of a pain. If we work mod 8, so in mod 8, Well, every integer exists in mod 8, but we're only going to concern ourselves with the least positive residues, the laziest numbers to work with. So what's the inverse of, oh, here comes Sean. Hang on a minute. Sean, get in there. Hi, Sean. I hope I didn't keep you waiting too long. I just turned my head and saw your name there.
That's right. Thank you, Professor.
Yeah. Hi, how you doing?
Good.
Now, you see 3 to the negative 1, right away, your mathematical upbringing, you think 1/3, but there's no such thing as 1/3. We don't have fractions in modular. So what's the inverse of 3 mod 8? 3 times what gives you 1?
1/3.
But we don't have 1/3. It has to be one of these. There's no fractions in the modular world. In regular arithmetic, this would be 1/3, but we're in mod. So 3 times what number produces 1 mod 8?
3.
Yeah, there you go. So 3 times 3 equal to 9, but that's 1 mod 8. So in this case, 3 is its own inverse. 3 times 3 is 1 mod 8. How about 5? And I'm just going to be writing 1 now because it's understood we're in mod 8. So what times 5 gives me a 1? Big hint. It has to be one of those numbers.
5.
Yeah, again. So in mod 8, 3 and 5 are their own inverses. How about 6? What times 6 gives me 1 mod 8? And it's got to be one of those numbers. Well, let me put it this way. If an inverse exists mod 8, it has to be one of those numbers. So you can do what's called brute force. You can just check every single one and see if you get a multiple of 8 plus 1. So 6 times 1 is 6. Nope. 6 times 2 is 12, but that's 4 mod 8. 6 times 3 is 18, and that's 2 mod 8. 6 times 4 is 24. Well, 6 times 4 is 24. That's negative 1 mod 8, but we're not using negatives. 6 times 5 is 30. So 6 times 5 is 30, so that's 6 mod 8. 6 times 6 is 36. Divide by 8, you don't get 1. 6 times 7 is 42. That's 2 mod 5. So in this case, 6 inverse in mod 8, 6 does not have an inverse. This is why when we do crypto systems, you don't use numbers that aren't prime. It might decode and not even exist. How about 7? Does 7 have an inverse mod 8? What times 7 gives me 1 mod 8?
7.
Yeah, 7. Look at all that arithmetic I'm making everybody do today. It's Monday. All right, so in mod 8, the only elements of mod 8 that even have a multiplicative inverse are 3, 5, and 7, and they are their own inverses. That's it. Nobody else has an inverse here. So that you can't do things with mod 8 and in modular world. So coming up with these, right? All right, let's try this. Let's work mod 11. There we go. Now, in mod 11, so those are the least positive residues. In mod 11, because it's prime, not because it's odd, because it's prime, every element will have an inverse. Finding them can be kind of really tedious, though. All right, so let's see. Let's take, well, and 1 is always its own inverse, so that's fine. So we take the number 3. And again, I'm not writing congruent mod 11. It's understood that we're working mod 11. So what times 3 gives me 1? And it has to be one of those numbers, and it is one of those numbers.
4.
So 3 times 4 is equal to 12. 11 goes into 12 once with a remainder of 1, and 4 times 3 is 1. So they commute. But in modular multiplication, commutativity always works anyhow. So they are inverses of each other. You can say that 3 is the inverse of 4. You can say that 4 is the inverse of 3. Where you put the negative 1 doesn't matter. How about 6? What times 6 gives me 1? Lots of arithmetic.
2.
2, yeah, so 2. 6 times 2 is 12, just like 3 times 4. So 6 and 2 are multiples of each other. 5. It's a lot of arithmetic. It's good for us, though. So what times 5 gives me 1?
9.
So 5 times 9. 5 times 9 is 45, and 45 is 1 more than a multiple of 11. So 5 and 9 are inverses of each other. 11 is kind of nice to work with because the multiples are so easy. 11, 22, 33, 44, 55, and so on. Okay, now, if we allow ourselves to go beyond the residues, then each one of these elements, and we can go negative, you can have negative and positive, then each element has an infinite number of inverses, which is why that coding and decryption works. So let's look at exponentiation. Exponentiation just means raise things to an exponent. So if we do, so 3 to the first is 3, and we're working mod 11 here. 3 squared is 9. 3 cubed is 27. 3 to the fourth is 81. 3 to the fifth is 3 times 81, but we don't have an 81 mod 11. So, and we don't have a 27 mod 11. So this is actually 5. So 3 to the third power is 5 mod 11. 3 to the fourth is 81, but we don't have an 81. So 3 to the fourth is 3 times 3 cubed. So 3 to the fourth, and we've done some of these before, 3 times 5 is 15. So this is actually 4. 3 to the fifth is 3 times 3 to the fourth. So 3 times 4 is 12, and it's 1. So there we go. So 3 to the fifth is 1. So 3 times 3 to the 5th is 1 mod 11. So 3 to the 5th is another inverse of 3, but 3 to the 5th just reduces down. Also, we also know that 3 to the 10th is 1. So 3 to the 5th gives me 1. 3 to the 10th gives me 1. And this is, that's Fermat's little theorem I talked about. I think it was last time. 11 is prime. 10 is 1 less than 11. So any of these numbers to the 10th power give me 1 mod 11 because of Fermat. But here's another one that gives me 1. So we see from this, so if 3 times 3 to the, if 3 times 3 to the 5th is 1, and 3 times 3 to the 10th is 1, then 3 to the 5th is equal to 3 to the 10th. And remember, this is all mod 11. So round and round and round and round we go. So what about 3 to the 15th? Well, yeah, that's going to be 1 also, right? So 3 times 5 times 3 times 10 is equal to 3 to the 15th. But 1 times 1 is 1. So 3 to any multiple of 5 is going to give you 1 mod 11. So there's all kinds of patterns happening here. Round and round and round we go. So in this case, 11 is a small number. Finding an inverse can be really tedious, especially if your prime numbers have 10,000 digits in them. So you have a prime number with 10,000 digits in it, and you have a number, so, you know, or even 1. So mod 101, which is prime, what's the inverse of 73? Finding that is very difficult. And that's another way that that encoding system we used last time can be worked. Instead of, excuse me, when we did our modular encryption system, we took a number, like a letter. So C was 002, and we added multiples of the mod to it to come up with an encoded word. But you can also take a letter from the alphabet, and instead of adding, you can raise it to an exponent and encrypt it that way. And to decrypt it, you need the modular inverse of that exponent. And that's the basis of what's called the RSA, or public key encryptions. And we're not going to get into that, but just some of you will have that in your future. I'm going to send you, for those of you who are interested, if you're going into like cybersecurity and all that, I'm going to send you a write-up I've done of the RSA public key code and how it works. It's very mathy looking, but at this point, there's module, you can read it really well. If we were in a classroom, we would be doing it, but it's too awkward to try and do it over a Zoom camera on here. All right. So this is also group theory, by the way, but we're not going to have just numbers. A group, instead of numbers, you just have elements. So we know sound frequencies together with the binary operation of addition is a closed set. No two sound frequencies added together are going to give you something that's not a sound frequency. It's closed. This system is closed. Colors work the same way, right? A color plus a color is a color. We all know that, what do green and yellow make? Any visual artists out there, color wheel stuff? What do green and yellow make when you add them or layer them? Anybody remember? well, that stuff and take
Blue.
yeah, so green and yellow equals blue, right? So here, and then there's an inverse. So the inverse maybe you can think of as either black or white, depending on how you're doing it. So here, by addition, we're talking about layering. You take one translucent color and another, and you layer them on top together. So green layered with yellow would give blue. So here, the binary operator is called layering. But it shouldn't be surprised that a color plus a color is a color, because a sound wave plus a sound wave is a sound, is an energy frequency plus an energy frequency produces another energy frequency. And sound and color are just different frequencies of vibrations, right? So group theory will get into all of this kind of stuff. And it's not always true. You can have a group that's not closed, where your operator takes you outside that group. So where we're going to head up for this to finish off modular arithmetic on Wednesday, today's Monday, we're going to look at something called the Chinese remainder theorem. This gets used in computer science a lot when you're processing large numbers, and it's basically modular. I'll bet you can guess why it's called the Chinese remainder theorem. Guess where it was first sort of discovered? And it goes back a couple of thousand years ago, and there's a whole story that goes with it. But let me give you an example of where that gets used. So we're going to do, there's not enough time to do it today. That's going to be a whole class. Where am I here? Oh, nope, wrong one. Here we go. Okay. All right, so Godzilla's age, all right? Let me just... So Godzilla's age is X. When divided by 2, remainder is 0. So what does that tell us about Godzilla's age? When you divide Godzilla's age by 2, you get 0. So what do we know about Godzilla's age so far?
It's even.
It's an even number. Very nice, right? If you're working mod 2, and remember, we're only using whole numbers, the only remainders you get are 0 and 1, right? If a number's odd, divide by 2, you get a 1. If number's even, divide by 2, you get a 0. Zeros and ones, oh my goodness, binary, all right? When divided by 5, the remainder is 1. When divided by 7, the remainder is, hold on a minute, let me think. I don't want to make an arithmetic mistake here. Yeah. So divide Godzilla's age by 7, and the remainder is 3. When divided by, now notice I've used prime numbers so far. Don't always have to use prime numbers. If we divide it by, give me a second here. want to make one of my dumb arithmetic mistakes. Whoops, hold on. Oops, when divided by 4, the remainder is 2. All right. We can use the Chinese remainder theorem to determine, so how old is Godzilla? Now, this is a system of modular equations. This is all in words. The Chinese remainder theorem, well, Godzilla is Japanese, but that's beside the point. The story from thousands of years ago was this philosopher mathematician posed this question. This woman who's going around town selling eggs from a basket, if she hands out so many eggs, there's this many left. If she were to hand out this many. And so this is a system of modular equations. So I'm going to leave you with this. I'll write this up. So I'm going to send out some homework, just determining modular inverses. And I'll type this up. And by Thursday, you can try and figure out how old Godzilla's age is. And by the way, there's a correct answer. I'll tell you my definition of how we determine Godzilla's age when we get back. Now, there are an infinite number of solutions to this, but we're going to look at the smallest positive value of X. In other words, the least residue with all of these mods. So here's what this looks like as a modular system without the words. So what we have is X is 0 mod 2, X is 1 mod 5, X is congruent to 3 mod 7, and X is congruent to 2 mod 4. So without the words, that's a system of modular congruences. In other words, 4 equations, 4 unknowns, except the X is the same for all of these. So at some point you learned how to do 2 equations, 2 unknowns with X's and Y's and the lines crossed. This is the same kind of thing. In order to do the Chinese remainder theorem, we have to be able to calculate an inverse. So your homework tonight is just going to be finding some inverses and trying to figure out how old Godzilla is, and I'll explain all that next time. Let me see. Do I want to do anything else? No, that's all I really wanted to do today. Has anybody got any questions, comments, observations, opinions, goofy stories?
Do you teach Calculus 3? Are you going to teach it anytime soon, Calculus 3?
Who knows? We don't get to pick, like I've mentioned. They tell us. So along about sometime in April, they are contractually obligated to give us our schedules, although they're often late. Scheduling, by the way, is a nightmare. Different classes, different times. This person can't be here. This one, it's a nightmare scheduling. They used to let us just decide what we wanted to teach. The math department had 2 meetings. The first meeting was we all got to pick when we want to teach. We got to pick. It was so great. And then they did the time blocks. And then we had another meeting a couple weeks later, and everybody got to pick what they wanted. So you'd go round and round. The most senior people got to pick a course first, and you go round and round and round, and then that way everybody's mutually unhappy or thing. Because there was a time when everybody wanted to teach calculus, but there's only so many calculus sessions. So as the new person, it took a while till I finally got one. You get stuck with the yucky stuff for a while. So anyhow, to answer your question, I have no idea what I'll be teaching.
Okay.
I haven't done Calc 3 in, 3 or so years. We got some new people who are running the department, deans and assistant deans and all of that. And they tend to just roll schedules over from one semester to another because it's easier for them.
Okay.
And if you're really nice to them and slip some money, you can say, look, I haven't taught this course. I really want this course. And if you're on their good side, you might get it. So it's all politics. So I have no idea. I'll tell you though, for the longest time, Pezzamenti was teaching Calc 3 every semester. And he's really good at it, by the way, and he likes it. And that's a good combination to be good at something and like doing it. Finberg taught it for a long time, but she's not with us anymore. We have a couple of new people in the math department who are basically like real math people. They've full-blown PhDs, so they're probably going to jump on it a little bit too.
All right. I think Rebecca has a question.
Yeah, I see that. Homework. Oh, yeah. Okay. That's a good one, Rebecca. I'll show you that one. And I did one like that in class, but I'm going to do this one for you because it's pretty straightforward. Let me just pull it up here. Oh, okay. So you wrote out your own version of it, right? So which one am I looking at? I'm looking at where it starts out a definition, and then given that A is C mod M and all that, letters C. Oh, okay. Yeah, this is a good one. So the modular proofs that look like this all turn into basically just arithmetic. So they all kind of work this way. So I'll go through it. So given, so we're told this up on the top, and then there's various things. So for C, it's prove that AK is congruent to CK mod M. And K is a constant, an integer here. Well, first, let me take you back to like probably 6th or 7th grade. How can I rewrite 2 times the quantity of X plus Y? 2X plus what? Oh, I thought you said M. Okay, so early algebra. And equal signs go both ways. This is distribution and this is factoring. Well, really, that's what this is saying. So I'm just doing K times all that. But you got to prove it works, because in modular stuff, weird stuff happens. You can go this way in modular arithmetic, but you can't go this way unless certain situations are met. So there's an example in that homework to show you, you can't always cancel common factors. So here's how we prove this. We use the definition. We're going to take this out of modular and write it as regular arithmetic. So we can think of C as the remainder when A is divided by M. So A is equal to, now this is equal, real arithmetic, C plus M J. So you divide A by M, and this is the remainder. And then this is just a multiple of the mod. I'm using J. So this is regular old arithmetic here. So if I multiply by K, I can distribute that, and I get AK, equals, is equal to CK plus MJK. Okay, so far? Okay, now, so AK is equal to CK plus, and these are all integers. If you multiply 2 integers together, what do you get? You get another integer. So J times K is another integer. So let's just call that T. Oh. Well, by definition, this is AK is equal to CK plus a multiple of the mod. So therefore, AK is congruent to CK mod M. And that's the end of the proof, right? So it's just arithmetic, but you're using the definition of what that means. So by definition, and definitions are statements that are always true. You know, if I define up as that way, then all of the physics will make sense. But once I've defined up as being that way, that means down is that way. That's a Calc 3 thing, by the way, Kenneth. So it's just on the definitions here. So A, B, C all work like that, Rebecca. And D. So we know D is not true. And how do you prove something's not true? You only need to come up with, right, and E has that example. To try and prove, and I think it was Zane or Robert who tried to prove D in a general sense and got all messed up because you can't really disprove that generally because it can be true sometimes. So the only way to disprove that universal statement is by an example. Oh, I'm really glad you asked that question. So is that, you're like, oh, okay, I get it, right? Okay, yeah, good. So there's a couple, so A works the same way, B works the same way, just a little messier. And in the textbook from this section, there's a couple of other homework problems that look sort of like that. And she's got a few examples like that too. All right. Wow, a real homework question, thank you. So if you came in a little late, I goofed up on the modular decoding. The one with the shift 10 should be OKAY, not TKAY. I don't know, I counted wrong or something. Anybody got any other questions? Uh-oh, wait a minute. 1, 2, 5, 7. Oh, because I was going to send you the Godzilla thing. I just realized I erased what I had over here. So I'll send you out, for those of you who are interested, it's not homework, I'll send you out the algorithm and the proof of how the actual RSA code decryption works, and you can read that if you want. I think she does it in the book a little bit, but she does it in like 5 sentences, and I kind of stretch it all out for you. All right, then. I guess I'll see you all back here on Wednesday.
All right. Take care, Professor.
All right. Bye, everybody.
Thank you, Professor. Have a great day.
You too.
Thank you. Have a good day.
Have a good one.
So long.